video that will illustrate how to handle the situation of parallel pipes and replace them with an equivalent pipe. Okay, so the question here is below is a schematic of a pipe network with parallel pipes. Find the equivalent length in feet of a single pipe with a diameter 12 inches and a Hazen-Williams coefficient of 100 that carries the same total discharge as the three-pipe system. So I think the most useful way to deal with this is to express the Hazen-Williams equation in velocity form, compute it to a discharge, and keep in mind that the head loss from one end to the other end of the system is the same regardless of the path in a parallel pipe system, and we're going to replace those three parallel pipes with an equivalent single pipe that also produces the same head loss for the same total flow rate. So the velocity form of Hazen-Williams is V is 1.381 C sub HW, hydraulic radius to the 0.63 power, slope, and this is the head loss per unit length, to the 0.54 power. Multiply both sides of this by the area. We get area times velocity is equal to Q, and this is equal to 1.381 times pi d squared over 4 for whatever pipe we're in, C sub HW for that particular pipe, hydraulic radius to the 0.63 power, and slope to the 0.54 power. Okay, so this is the version that we're going to use. We're going to also notice that the slope is equal to the head loss per length for any pipe, and the hydraulic radius by definition is going to be the diameter divided by 4. So the discharge form becomes Q is equal to 1.381 times pi over 4 times the Hazen-Williams coefficient C sub HW times diameter raised to the 2.63 power over 4 to the 0.63 power. So I pulled the diameter out of the hydraulic radius times H sub L to the 0.54 power divided by L to the 0.54 power. Let's evaluate the constants that we can. Pi over 4 times 1.381 divided by 4 to the 0.63 power is 0.4528. Hazen-Williams coefficient, diameter to the 2.63, H sub L to the 0.54, pipe length to the 0.54, and so that would apply along any of those three paths. So now let's consider the three parallel pipes. Here's what we know. We know that the head loss is the same along any path. We also know that the total flow is the sum of the three flows A, B, and C. So let's express the total flow, which is going to equal 0.4528 C sub HW, diameter of pipe A to the 2.63 power, head loss to the 0.54 power, length of pipe A to the 0.54 power, plus 0.4528 C sub HW for pipe B, diameter of pipe B to the 2.63 power, head loss to the 0.54 power divided by length of pipe B to the 0.54, plus 0.4528 C sub Hazen-Williams, diameter of pipe C to 2.63 power, head loss to the 0.54 power, length of pipe C to the 0.54 power. And that's all going to equal 0.4528 C sub HW of, let's call it pipe total. So D total, 2.63, head loss to the 0.54, length of the total to the 0.54, where the total is the equivalent pipe. So let's do some algebra. 0.4528 times head loss appears in all elements, so these can be divided out. So if I divide the entire equation by 0.4528, that term, that term, that term, and that term divide out, and the head loss has to be the same. So that term, that term, that term, and that term divide out. So what I have left at this point, let's see if I can fit it in on this one sheet of paper. I probably can squeeze it in down here, and then I'm going to use this area up here to complete the work. So I have C sub H W for pipe A, diameter of pipe A to the 2.63, divide by the length of pipe A to the 0.54, plus C sub HW of pipe B, diameter of pipe B 2.63 over length of pipe B to the 0.54 power, plus C sub HW pipe C, diameter of pipe C to the 2.63 divided by length of pipe C to the 0.54 equals C sub HW of the total pipe to the 2.63 power divided by length of the total pipe to the 0.54 power. Technically, the only unknown is this guy right here. Every other term we actually have a value for. So let's substitute those. So this one is 110. Diameter is 8 over 12 raised to the 2.63 power. Divide by 1300 to the 0.54 power, and that's going to equal 0.7884. This one is 120, 6 over 12 to the 2.63 power, divide by 900 to the 0.54 power, and that's going to equal 0.4922. This one is 100 times 12 over 12 to the 2.63, divide by 1300 to the 0.54 power for a value of 2.0819. And so now we can sum these three. So 0.7884, 0.4922, and 2.0819 equals 3.3626. So I'm going to carry that up here and continue my work. I now have 3.3626 is equal to C sub H W T times diameter of T to the 2.63 over the unknown length of T to the 0.54. Rearrange this. I have length to the 0.54 equals C sub HW T D T to the 2.63 divided by 3.3626. Therefore, the length is equal to the 1 over 0.54 power of that thing. C sub HWT dt 2.63 power over 3.3626 to the 1 over the 0.54 power. And now we can put in the actual numerical values and attempt to do the arithmetic. I have 100 over 12 times 12 over 12 to the 2.63 power, divide by 3.3626, that whole result raised to the 1 over 0.54 power. That equals 29.7389 to the 1 over 0.54 power, which equals 535.03 feet. So that's my equivalent length. And technically we would be done. Now we can check that by running our Hayes and Williams discharge calculator 4 times. So let's just suppose head loss equals 20 feet. Give me a second. Let's see, I'm going to be US. Okay, so here is a calculator for head loss. And so we'll go for the first pipe, which has a loss coefficient of 110, a diameter of 8 divided by 12, calculator 0.66667. The length of that pipe is 1,300 feet. And if we enter a discharge of 1.8, I've obviously done the trial and error, we get a head loss. So if I put QA 1.8 CFS, that produces a loss of 21.65 feet. Now we'll repeat that for the next pipe. Pipe number B is loss coefficient of 120, diameter of a half, length of 900, and if we supply a flow estimate of 1.12, we get a loss of 21.51 feet. So if we do QB of 1.12, we get a head loss of 21.51 feet, about the same. Do the last one. 100, diameter is a whole foot, length is 1,300 feet, and enter a discharge of 4.75. We get a QC equals 4.75. That produces a loss of 21.62 feet, also about the same. If we sum all those, we get 7.67 is our flow rate. And so now we're going to apply the 7.67 through this length of pipe, and we should get the same head loss. So our loss coefficient is now 100. Our diameter is 1. Our new length is 535.03 because we're so good. And our flow rate is 7.67. And lo and behold, we get a loss of 21.62 feet. Therefore, we're quite comfortable that that's the equivalent pipe length that produces the same head loss as the 3 flows distributed among the 3 pipes. So here's the summary sheet. So this is what we just did with the simulator. These are the head losses, basically 21.5 feet for all 3 cases. Pipe A, B, and C added together in the total pipe produces the same head loss over 535. And that concludes this video.